Hello there. So let's take a look at the background for the Rates of Reaction lab this week. So we're talking about collision theory and how we can manipulate the speed of a chemical reaction by manipulating the collisions when they occur for the reacting materials. Now we're going to look at a couple of factors, but the main things that everything falls back to is the energy of activation, which is the minimum energy required for the chemical bonds to break, the sheer number of collisions, and the energy involved in each one of those individual collisions. If we can control these three main factors, we can control the speed of the reaction. Remember, that's all the energy going in bond breaking, and all the energy that comes out in the making of new chemical bonds. Remember also, for each of the reactions you're going to carry out, a maximum timing of 6 minutes or 360 seconds per reaction. If the reaction takes longer than this time, just put it down in your notes as 360 seconds plus and move on to the next reaction. For the last experiments on catalyst and surface area, just record the relative rate of bubbling for each version of the experiment. Do not try to record the time. You'll be waiting for hours. So the first thing we're going to look at is a state of reactance. We had learned in chapter 3 with ion chemistry that ionic compounds, when dissolved in water, are normally good at dissociating into individual positive and negative ions. They effectively break their bonds. This is also true sometimes for covalent compounds, predominantly for molecular acids like hydrochloric acid HCl. In water, they break their bonds into individual positive and negative ions. The hydrochloric acid dissociates into hydrogen ions and chloride ions. We now know from chapter 6 in equilibrium chemistry that often these reactions are reversible. The hydrogen ions and chloride ions can recombine back into the original hydrochloric acid molecule. So when the position of equilibrium is firmly on the right, meaning that we have mostly these hydrogen ions and chloride ions, we say that hydrochloric acid strongly dissociates because it's a dissociated form that predominates. That should lead to a fast reaction because when the hydrochloric acid reacts with the other chemicals in the reaction, mainly the magnesium and the zinc, the bonds of the hydrochloric acid are already broken, and so there's no energy of activation energy to overcome. Meanwhile, for acids like acetic acid, although it can break up to give us hydrogen ions and acetate ions, we see the position of equilibrium is firmly on the left. It's not very good at dissociating, so at equilibrium there's only a small number of these dissociated hydrogen and acetate ions, and most of the chemical exists in this pre-bonded form. We therefore say that acetic acid is weakly dissociated. Any reaction with magnesium or zinc still has to break these bonds, and therefore the energy of activation will still be high. So by dissociating, by breaking their bonds, the energy of activation for chemicals like hydrochloric acid has been lowered to this new level. Now when the molecules collide, it takes less energy for an effective collision and the bonds to be broken. Meanwhile, for the acetic acid, that energy of activation remains high, making it more difficult for the collision to have the required energy, and therefore more difficult to break the existing bonds. We see no change in the number of collisions, no significant change. We see no change in the energy of the collision, how fast the molecules are moving. That increased speed of reaction rate is all about lowering the energy of activation when these chemicals dissociate in water. So the reactions with faster reaction times are the ones where the chemical has dissociated strongly and the energy of activation has been lowered. Next, you'll look at concentration, changing the concentration of the hydrochloric acid. At lower concentration, the molecules don't collide with each other as much. Meanwhile, if we increase the concentration by increasing the molarity, things are more congested. Molecules will collide with each other more frequently. Now, not all of the collisions will have the energy required to break the bonds. They will not have the energy of activation. If there's a sheer greater number of collisions, statistically, we should see more collisions which have the energy of activation and therefore a faster reaction. This is different from what we said about the state of the reactants. We're not increasing or decreasing the energy of activation. It's still the same energy requirement for bonds to be broken. But with a higher concentration, more of the collisions will have that energy. Looking at the effect of temperature, the effect is actually twofold. Reactions carried out at lower temperature should have a very small number of collisions which meet and surpass that energy of activation requirement, and therefore the rate of reaction will be slow. But if we carry out the reaction at high temperature, there's a twofold effect on the rate of the reaction. For one thing, with the molecules moving faster, we're going to see a greater number of collisions. Sheer number of collisions increase, which statistically should increase the number of effective collisions. And because the molecules are moving faster, when they collide with more kinetic energy, and therefore more of the collisions will have the energy of activation. Again, we're not changing the energy of activation. We're changing how many of the collisions have the energy of activation when temperature is increased. So we should see a faster reaction and therefore a shorter reaction time period when we raise temperature. If we look at a change in surface area, taking a big block of chemical and grinding it up into smaller pieces, that should change the amount of surface area in the sample. It will increase the amount of surface area. So the volume to surface ratio has been increased. Same volume of chemical, but more chemical exposed at the surface. We should see an increase in the number of collisions and therefore an increase in the rate of the reaction. No change in the energy of activation, no change in the speed of the molecules. That only normally happens with a change in temperature. We can also add a catalyst to the reaction. As we've said in the notes, adding a catalyst lowers the energy of activation. We're providing a surface for that vital collision to occur, and so there isn't as much energy required for the collision to be effective. We increase the rate of the reaction with the addition of a catalyst by decreasing the energy of activation. Remember, the catalyst itself is not changed by the reaction and so can be used for other chemical reactants to further the reaction. So we only need a small amount of the catalyst. Remember, waste disposal. All of your waste today should go into the metalline waste. That bottle is sometimes marked as the inorganic waste for non-lead, non-chromium waste. If you're not sure, just ask me during class.